everybody, it's June 5th and it's time to get started on our reduction and oxidation unit. Today's focus is how can we tell if a reaction is a redox reaction? And these are the two steps we need to take. Number one, we need to assign oxidation numbers to all reactants and products. And number two, if there's a change in the oxidation state, then there is a redox reaction. So let me warn you, not all reactions are redox reactions, and that's why we're going to need to assign these oxidation states to all of the species. So when we look carefully, sodium can only be a +1. Chlorine has many options, but it must be the -1, and therefore we have a net zero charge. We look up silver. Silver can only be a +1 oxidation state. Nitrogen, I'm going to skip over that because it has many options. Oxygen can only be -2 though. So we have a -6. We have a +1. This must be, right, +5 to give a net zero charge. We go over here to our product side. Silver is a +1. Chlorine is a -1, net zero charge. We move on to sodium nitrate. Sodium has to be a +1. Oxygen has to be a -2, giving us a -6. Nitrogen is a +5. Here we go. Now, we've assigned all oxidation numbers. Let's compare. Sodium has not changed its oxidation state. Chlorine has not changed. Silver has not changed. Nitrogen has not changed, and oxygen has not changed. This is not a redox reaction. There's no change in the oxidation states. Let's look at another example. According to our rules, zinc is a free element. It will always have a 0 oxidation state. Hydrogen has a +1. Chlorine has many options, but this formula tells us it's a -1. Net zero charges. Our zinc chloride, you'll notice zinc only has +1 as an oxidation state. Chlorine must have a -1. That 2-to-1 ratio when we wrote that chemical formula many months ago. This is a net zero charge. And finally, we have hydrogen gas. Diatomic elements are always a 0 oxidation state. Let's make this interesting. We have a redox reaction. How do I know that? I'm going to start comparing. My zinc has changed its oxidation state. It's gone from a 0 to a +2. That means zinc must have lost electrons to become more positive. It had a loss of how many? 2 electrons. Leo. Loss of electrons is oxidation. Zinc is oxidized. Let's continue looking. Hydrogen. Oh, here we go. Hydrogen changed from a +1 to a 0. It's becoming more negative. It must have gained, or a gain of 1 electron must have occurred here. This is GER. Hydrogen gained an electron to become this hydrogen gas. It is reduced. Finally, let's look at chlorine. -1, -1. Chlorine has not changed its oxidation state, We're really not interested in chlorine right now because in redox reactions, we're following the transfer of electrons, and that's shown here right now. So the loss of electrons is oxidation. The gain of electrons is reduction. Let's write what we call a half reaction. I've got a redox reaction here. I want to write the oxidation half reaction and the reduction half reaction. So let me show you how that happens. The first thing we do is we write a partial half reaction. So let's look at zinc. Zinc with no charge. Zinc with a 0 oxidation state became zinc plus 2. Zinc lost 2 electrons. So I'm going to write that on the right-hand side. This zinc was oxidized to become zinc plus 2 plus the 2 electrons that it lost. Let's look at our hydrogen. Our hydrogen plus 1 became hydrogen 0. How did it do that? It gained 1 electron. 1 electron was gained by this hydrogen to become that hydrogen. Ultimately, our half reactions need to be balanced in terms of charge. If I've only got 1 electron here and 2 here, I need to balance this equation in terms of electron charge. So I'm going to multiply all of these species by 2. 2 electrons are gained for every 2 hydrogen ions to make that 2 diatomic hydrogen. We now have the balanced charge. If I just summarize without my electrons now, I would say 2 hydrogen ions plus that zinc yielded the zinc ion plus that hydrogen gas with no charge. So to conclude, we determined that we have a redox reaction by assigning oxidation states to each atom. Because there were changes in oxidation states, we knew that this was a redox reaction. We then go and we write half reactions where we're only dealing with the species that had changes in oxidation states because we're tracing these electrons. And ultimately, we balance the half reaction by making the charge equal. And sometimes you have to multiply one of the half reactions, as in this case. And then I can summarize it all right here. Let's look at a third example. Now, this example's showing ions only. So sometimes, because all we really care about is following these electrons, sometimes you're not going to have full chemical formulas written out. We're only going to show the ions. And right off the bat, we can see that iron 2 becomes iron 3. So we know that iron has changed its oxidation state, and same with cerium. Let's connect that. Iron 2 has become more positive. Therefore, it must have lost 1 electron. That is Leo. Loss of an electron, it's oxidized. This is oxidized. Cerium, on the other hand, had to grab an electron. It went from +4 to +3. It's getting a little less positive. Why? Because it had a gain of 1 electron. That is the GR. It is reduced. So cerium is reduced. Let's write the half reactions for that. We just take our iron 2 plus. It became iron 3 plus. Our cerium 4 plus became cerium 3 plus. Iron lost 1 electron, so I'm going to write it on the right-hand side. This lost an electron. It gets written on the right-hand side. This species gained an electron to become this species. And we write it there. Our net result is shown right up here. This is the oxidation half reaction. This is the reduction half reaction. Let's look at our final example for today. We've got copper, that is a free element with a 0 charge. We've got silver with a +1, that's its only option. I'm skipping nitrogen because it's got so many options. Oxygen has a -2. We have -6. +1, our goal is to have a net 0 charge. This must be a +5. Okay, we look here at our copper. Well, copper has multiple options here. So I actually can identify which oxidation state that copper is, because in writing this formula, if you recall, in the crisscross method, we had to do that. Right? The +2 had to go down here. So I actually do know the oxidation state in this case. Our oxygen is always a -2. So over here, we actually have -6, but we have 2 -6s. That's a -12 for that oxygen. That copper is only +2. Our nitrogen, we want to be a +10, right? To get a 0 charge. Well, we've got 2 nitrogens. It must be +5 for its oxidation state. And finally, silver as a free element is a 0 charge. Do we have a redox reaction? You betcha. Our copper has changed, and you'll notice our silver has changed, and our nitrogens and oxygens are not of much interest to us. They have not changed. So copper has lost 2 electrons to go from a 0 to a +2 charge. Therefore, it's oxidized, Leo. Silver must be reduced, right? It had to gain 1 electron to go from a 1 to a 0. It's reduced. So to write this half reaction, we make it real simple in the beginning. We just say Cu0 became Cu +2. Ag +1 became Ag0. If we lost 2 electrons in our oxidation, we're going to write that here, 2 electrons. We've gained 1 electron here in our reduction half reaction. Oxidation half reaction, reduction half reaction. We need to balance the charges. We have 2 and 1 here. We're going to multiply this by 2. So it's going to be 2, 2, 2. To summarize it all, we have Cu0 plus 2 plus 2 Ag positives yields Cu +2 plus 2Ag0. Our net expression just doesn't show the electrons in the end. That concludes this lesson. I hope you enjoyed it. Have a great day. Bye.